Hello everyone, welcome to our video on the 7 pillars of statistical wisdom. In this video, we'll delve deep into the seventh pillar, residual. Our team comprises Yash Deshpande, Eldho Babu and Vivek Yadav. The whole video is organized as follows. We'll first have an introduction to the 7 pillars of statistical wisdom, followed by an introduction and mathematical formulation of residuals, a mathematical understanding of residual with an example, the history of residuals, difference between residual and error, the importance or significance of residual, and the conclusion. What are the 7 pillars of statistical wisdom? The Seven Pillars of Statistical Wisdom is a book authored by Stephen M. Stigler. The Ernst Dewitt Burton Distinguished Service Professor Emeritus of Statistics at the University of Chicago in the United States. The book was published in the year 2016 by Harvard University Press. The book actually is important because it outlines the core fundamental ideas which are very significant to the field of statistics. And Stigler quotes, the pillars are the support, not the substance of statistics. What does this quote mean? This quote underscores an essential point in statistics, that is, the foundational and fundamental ideas and principles matter more than the particular methods or tools that are employed by a researcher in the analysis of data. The pillars symbolize the essential frameworks, such as the statistical approaches, calculations, or the softwares you use that aid in the statistical work, whereas the substance is found in the deeper statistical concepts, reasonings, and interpretations that give the real meaning to an analysis rather than the tools we use. And the seven pillars comprise aggregation, information, likelihood, intercomparison, regression, design, and residual. Altogether, these seven pillars define statistics as a very special scientific field that is quite distinctive from other fields such as mathematics or computer science. So these seven pillars give a unique definition to the area of statistics. Let's discuss about residuals. So, what are residuals is a very important question because we're discussing about the seventh pillar now. The term residual can be understood as a difference between the observed value and the predicted value in a sample distribution that is to be noted. If it is a particular difference regarding the observed and predicted value of a population, we call it error, not residual. So, what does residuals do? How does a residual analysis help a particular researcher? This is a very powerful statistical tool or technique that is used to assess the performance of a regression model and the goodness of a regression model, and it also helps to identify the areas of improvement in a particular model. In a nutshell, we can see that a residual analysis can help us identify the accuracy of a regression model. In simple terms, a residual is what is left over after you try to explain something using a model or theory. Something left unexplained by a model or theory can be called as residual. So, in the statistical terms, it typically means that the residual is the difference between what you observe from your data and what is predicted by your particular statistical model. And how is residual important in science? It helps us see what our explanation our model doesn't account for. That is what we discussed in the previous point. What is left unexplained, the leftover or residual part, it can help you understand or uncover or unravel new insights or mistakes in our theories or models. Let's have a mathematical formulation of the particular concept of residual. Residual is equal to actual value of y minus predicted value of y. We've already discussed in the previous slide that residual is the difference between the observed and the predicted value. So, what is meant by the observed or actual value? That is the actual data point measured or recorded in the study. That is the responses we obtain from the respondents after the data collection, the actual data point. And what is the predicted value? Predicted value is the value that is estimated or calculated by the particular regression model or any other such predictive methods for the same data point. This can be made very simple with the help of an example, that is a mathematical understanding. Imagine a student is studied 5 hours per day. We can see in this, he studied 5 hours per day. And in the 5 hours of studies, the student scored a GPA of 8.5. And the regression model predicted that if a student studied for 5 hours, he would score, or he or she would score a particular GPA of 7.8, which is shown on the green mark. The red is the particular data point corresponding to the actual GPS score, that is 8.5, and the green color mark is actually regarding the predicted GPA by the regression model. And the difference between these two can be explained by y minus y hat. So here, the actual GPA scored is 8.5 and the GPA observed, or the GPA predicted by the model is actually 7.8. The difference is 8.5 minus 7.8. That is zero point 0.7 is the actual residual. That is actually the difference between the actual GPA and the predicted GPA. And the next slide will be about the history of residuals, which will be discussed by my colleague.
Thank you, Eldho. Let us begin by exploring the historical background and the evaluation of concepts of residual, which has been fundamental to scientific inquiry and statistical modeling. If we can see the history, in 1831, John Haskell, a prominent scientist, articulated a key scientific approach. Now we can know it as the method of residuals. He emphasized that in studying complex phenomena, start, scientist starts by explaining all known causes. What remains unexplained, he termed these as a residual phenomena. Inspired by Haskell's work, in 1843, John Mill formalized this method as one of the four fundamental methods of experimental inquiry. Mill recognized the power of focusing on residuals to uncover hidden causes in nature that might not be initially obvious. The concept of residuals found early practical application in the physical sciences as well. For example, in 14th not in 18th century, scientists sought to determine whether the earth was perfect square or not. They measured arc lengths along different latitudes. The simple model predicted equal arc lengths everywhere, but the observed differences residuals suggested that the earth was actually ellipsoid and slightly flattened at the poles. After that, Roger Joseph also visualized and plotted these residuals in 1770, providing an early example of residual analysis through graphical means. Later, in the late 1700s, anomalies in planetary motions, specifically those of Saturn and Jupiter, challenged the Newton's two-body gravitational model. By examining the residual effects, differences between the predicted and observed positions, scientists like Euler, Lagrange, and Laplace introduced the concept of three-body interaction. Laplace's work revealed these residuals followed a periodic cycle of 900 years, explaining the observed irregularities. By the 19th century, the scientists widely accepted the utility of comparing simple models with more complex ones, interpreting residuals to identify where the models could be improved. This era saw the beginning of statistical testing based on residual analysis. In 1899, the social scientist G. Euler used residual reasoning in the regression study of poverty and welfare relief. By accounting for multiple factors simultaneously, Euler employed what became known as multiple regression analysis. Residuals in this context revealed the portion of poverty unaccounted for by welfare, refining the understanding of social causes. Later, the Ronald Fisher in 1920s introduced the formalized concept of parametric models, families of models defined by specific parameters. This advanced the use of residuals by distinguishing between the random variation and the meaningful deviations, which making an model evaluation more rigorous. Following this, Newman and Pearson developed hypothesis testing methods, including the famous chi-square test, to evaluate the fit of the models based on observed residuals. A well-known example is Pearson's early 20th century dice experiment, involving over 26,000 trials where residuals between the observed and theoretical frequencies were analyzed comprehensively. By the late 20th century, the statistical models become even more sophisticated. Concepts such as generalized linear models and partial likelihood models extended residual analysis to a wider range of data types and model comparisons. Residual based tests continued to serve as critical tools to judge whether the more complex models genuinely improve explanatory power or not. More or less as a historical part, we can say that the historical developments of residuals from Herschel's foundational logic to the advanced model statistical models illustrate their central role in the scientific discovery and the ongoing refinement of models in both natural and social sciences. Moving to the next slide, now we will clarify the most important difference between the two fundamental concepts, that is errors and residuals. As you can see in the table, first of all, what is an error? An error, sometimes we call it as a disturbance, is defined as the difference between an observed value and a true value predicted by the correct model for the entire population. For example, if the true average height of 21 years old male is 1.75 meters and one individual measures it as 1.8 meters. Here, the difference, or we can say that the error between them is plus 0.005 meters. Errors are theoretically in nature because they relate to the entire population. And since the true values are generally unknown, errors cannot be directly calculated. They represent the deviation we should expect if we had perfect knowledge of underlying the relationship. Additionally, the errors are typically assumed to be independent across observations and their sum is dataset is not necessarily zero. On the other hand, What is residual? A residual is the difference between the observed value and the value predicted by our estimated model, which we construct from available sample data. Unlike errors, residuals are observable because they make use of fitted values or sample that we can calculate. In regression analysis, residuals are particularly important. One key property is that their sum is always zero. This is because the model fitting process ensures that the residual balance out across the dataset. However, residuals are not independent. Errors provide a theoretical measure of deviation from the true population model, but they remain unobservable. Whereas the residuals serve as a practical, computable estimates of these errors based on the model we fit to our data. They are essential tools for diagnosing model adequacy and guiding improvements, although they do not reveal the true unobserved errors directly. Moving on to the next slide, now we will see the how residuals are important in this modern world also. Residuals play a vital role in statistics and many real world applications. If we can talk about the statistics, residual help us check how well a model fits the data. By looking at residual patterns, we can detect if the model is inappropriate or appropriate. Randomly scattered residuals mean the model is fits well, but recognizable patterns or large residuals may signal problems like missing variables or wrong model choices. Residual also help identify outliers, which are unusual data points that can skew the result. They allow us to verify key assumptions such as constant error variance and independence, ensuring our model's reliability. When residuals reveal issues, they guide us to improve the model, for example, by adding new variables or transforming data. In the modern world, residuals are crucial for comparing the models. Models with similar pattern free residuals are generally preferred. Also, the residual help balance model complexity. They warn against the outfitting which happens when the model fits the training data perfectly but works poorly on a new data. Residual analysis validates that the models before they are used for decisions or predictions. Beyond the academic purpose, residuals are also very much important in today's industry perspective. For example, in manufacturing, they help to predict the machine failures by detecting abnormal behavior early. In quality control, residuals identify the defects by flagging unexpected variations. In finance, traders analyze residuals to spot market anomalies and opportunities. In the marketing teams, use residuals to find the customer groups not well explained by models, improving targeting strategies. As a part of healthcare, residuals helps in predicting patients' risks and spotting emergency health trends. More or less, in a summary, we can say that the residuals are the central to building better and more reliable models. They turn abstract statistical theory into practical tools to discovery and error detection, which saving our time, money, and sometimes even lives. Residual act like a magnifying glass, showing us that the models miss and helping improve outcomes across many fields. Moving to the conclusion part of our presentation, we can say that the key to better models and deeper insights is nothing but the residuals. Remember that the residuals are not much more than just differences between the observed and predicted values. They are the fundamental tools that guides us in understanding whether our models succeed or they fail. By carefully analyzing the residuals, we can detect patterns, uncover hidden problems, and refine our models to make more accurate predictions and better decisions. In the today's data rich world where models are becoming increasingly complex, residual remains a powerful lens helping us connect mathematical theory with the messy reality of the world. Whether in science, business, or technology, mastering residual analysis is a key to building trust in our models and ensuring reliability in our insights. At the end of our presentation, thank you for your attention. I welcome any questions or discussion on how residual can further improve your data driven work. Thank you.